This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So this week, Thursday, will be mid-semester exam. Do you know where the lecture, the venue will be? Okay. So this lecture, we are going to talk about quite important concept is Laplace transform and Z transform. Before I start, I want to, again to revisit what we have learned so far. So now it's chapter 7, and then we will have chapter 8, which is transfer function, and then we will talk about state space. So according to the chapter numbers, we are very close to the end of the subjects, though it's just week 7. Okay. I think a lot of people organize these subjects in different way, and some people start from Laplace. And you have to know Laplace transform was invented by a mathematician trying to solve the ordinary differential equation. So the concept of Laplace transform is very powerful, not limited to the engineering applications. And the engineers, most engineers, they like use from Fourier transform. So let me first think about, okay, chapter 1, we did a brief introduction of signals and systems. Gave a lot of definitions, and you see the questions about check whether this system is linear time invariant or time varying. And we also talk about continuous time signals and discrete time signals. This is chapter 1. Chapter 2, basically we were talking about convolution definition in time domain. So we start definition of convolution. You have to remember chapter 1 is introduction, chapter 2 is about system, which find the solution of system use the concept of convolution. So the very important concept is convolution, and we teach you how to do convolution in time domain from discrete time signal first, continuous time signal. Then chapter 3 is my Fourier series expansion, which basically talking about periodic signals. And then we generate this idea from periodic to non-periodic signal. We come to the Fourier transform. And then we will consider from continuous time to discrete time. We will have continuous time Fourier transform, discrete time Fourier transform, and also when I'm consider finite numbers, I will consider, because most of engineering signals are finite. So it's kind of only finite value are not zero. You don't consider t goes to minus infinity, you don't consider the case t goes to infinity. So if you consider finite duration, it will be just finite duration. Then you will consider discrete Fourier transform. It's a sampled version of discrete time Fourier transform. And last week, Jamie talked about frequency analysis. So what he talked about, it's basically the concept of convolution in frequency domain. So if you consider this one, you can always consider chapter 2 and chapter 6. They are mirror. They talked about same thing. Chapter 2 is talking about in time domain, while chapter 6 is talking about in frequency domain. They are very similar concepts. And now we consider, okay, we will consider the Laplace transform, and for the continuous time signal, we will consider the transform for discrete time signal. So before I start, let me just revisit what you learned from chapter 6. So when we talk about frequency analysis of systems, we were talking about the case where convolution is used. Okay. So if you consider this is a system, I'm consider linear time varying system. Here is my input signal. Here is my output signal. Here is my impulse response. So in frequency domain, we will see that my y omega is my v omega multiply my h omega. Am I correct? Careful. Am I correct? Why? Okay, so, all right, so I'm saying it's multiplication, all right? All right, do I need to make sure this signal? Okay, so you have to consider now V and H. Okay, my VT is my input signal, and HT is my impulse response of a system. So HT is somehow representing a system instead of a pure signal. In this case, we have to make sure that I do this, my Fourier transform of this system in terms of my impulse response should exist. Yes?
Because it's an LTI system, shouldn't the integral be from 0 to infinity?
Yeah.
Doesn't make a difference. Right?
Yeah. So basically, you also need this one. If you consider linear time invariant, you just consider from t 0 to infinity, right? So that's also indicate, this condition is indicating as t goes to infinity, my impulse response will go to 0. And you can always consider the signal. You have an electrical circuit. You switch on and off quickly, and it will on and off. It will be constant or sometimes 0. And if this condition is not satisfied, just like my magnetic levitation try, so I switch on and off, I will have magnetic force, but the force is not enough. My gravity will dominant, and the system will go down, and it causes unstable. So in this case, if you look at lecture notes carefully, for this part, it says a stable, linear, time invariant system, so that this condition, this equation is satisfied. It's for stable, linear time invariant system. Okay, you have to know why we can't use generalized Fourier transform for the impulse response. Why? Because we can handle signals, but generalized Fourier transform cannot directly apply to a system. And you know, Vt is signal, Yt is signal. I'm representing my system by my impulse response. So this one is slightly different. I have to highlight. So I can always have my step response, my input signal is step, and I can calculate things. But if I want to represent my system into impulse response, represent system linear time invariant system, I don't want to use the generalized Fourier transform. In frequency domain, I only can handle a stable linear time invariant system. That means my impulse response as t goes to infinity will be 0. So you can see that Fourier transform, from its own definition, we need conditions to guarantee that my Fourier transform exists. So in the case, we see many signals, we don't have this condition. Step signal does not satisfy those conditions. Any periodic signal does not satisfy this condition. So how can we handle this one? We convert everything instead in omega, which my frequency domain, I will change to the Laplace domain, which everything is well defined under very tricky conditions. So let's first introduce Laplace transform. So you can see here, first, if you look at this one, it's continuous time Fourier transform. You basically say the frequency response of linear time invariant stable system is the continuous time Fourier transform of its impulse response. So you need to find this for a linear time invariant stable system. And we also use continuous time Fourier transform to analyze spectrum of signal, and there are conditions to guarantee a normal continuous time Fourier transform exists. So for a lot of signals, we have those conditions are not satisfied. We have to use Laplace transform and this transform. And here is the definition of my Laplace transform. Look very similar to Fourier transform. So Fourier transform here is j omega t, and now I represent this system in st. And you can see that all the transformation we learn is convert signal in time domain, which is a real value, into a signal in a complex number. If you consider my Fourier transform is a complex number. You have real part, you have imaginary part, you have amplitude, you have phase. And the same here, and xt is time signal, it's real signal, t is signal. So the difference between Laplace and Fourier is, in my Fourier transform, my variable here, omega, is a real number. So if you consider this one is continuous in omega, my omega is a real number. However, when you consider this case, because I know this is very similar to Fourier transform, this transformation should be a complex number as well. And this one is real number, t is real number. So only complex number coming from is my s. So my s is a complex number. So why this is important? Okay, let me explain a little bit later. So you can see here, normally people will talk about Laplace transform. We consider the case with my t from 0 to infinity. So this depends only on the value of signal for t larger or equal to 0. And this is very useful when you consider the differential equation with a specific initial condition. So that's why I told you Laplace transform was invented by mathematicians to solve the differential equations, particularly linear time invariant differential equations with any initial condition. So now we can write down my xt and its Laplace transform xs. This is Laplace transform pair. Okay, so why? Why introduce S will give you better performance? Because we are dealing with the same thing. We are dealing with the same thing of improper integral from 0 to infinity. How should you guarantee this one exists? Okay, let me do a very simple example. Okay, so I will consider my xt is constant 1. Okay, when I'm doing Laplace transform, I will use definition. So I really don't like the improper integral. So I will try to redo this one. I will consider this one will be my capital T, and I want this capital T goes to infinity. So what I'm doing here is I transfer this improper integral to the proper one, and consider any capital T is my interval from 0 to capital T. And after I do this integral, I will take the limit, this capital T goes to infinity. Question? All right. So this one is easy. I will take this part, T goes to infinity. And this one, I will have my S minus 1, E minus st, and 0 to capital T. Okay. So, okay, when this small t equal to 0, it will be 1 over S. So because it will be minus, I will use this one minus this one. So I will have 1 over S minus limit t goes to infinity minus E st divided by S. Am I correct? So if my S, I will write down my sigma plus j omega. Okay. Because my x is a complex number, I will write down its real part and imaginary part. So if my sigma is equal to 0, my sigma is equal to 0, I will see this will be exactly same as my Fourier transform, and if any signal smaller than 0 will be 0. So if my sigma will be 0, this transformation will be same as my Fourier transform. Now, you can see here, this is a very tricky thing. All right, so I'm writing down E minus sigma plus j omega and this capital T, and my T, I will consider limit t goes to infinity. So I'm writing down this case, and this one will be limit t goes to infinity e minus sigma t and e minus g omega t. Why I write down in this form? Because I know for this term, okay, no matter how big my capital T is, the amplitude of this one will be always 1. Okay, so this one doesn't cause any trouble. Okay, so this limit exists if my sigma is positive. So if my sigma is positive, I can find this limit easily. And this limit will be 0. Okay, so you can see this case, even in this situation, I'm dealing with an integral which is an improper integral, but by playing with my real part of my s, sigma, I can always guarantee that this integral will exist. So, if I'm doing this one, I will see, okay, from here, if my sigma smaller than 0, then I will have my xs will be 1 over s. Okay, do I limit anything related to my signal? No, there's no requirement of the signal. Because if you do the Fourier transform of constant 1, you don't have a solution. Because it doesn't satisfy integral from minus infinity to infinity 1 dt will be less than infinity. However, when I play with Laplace, okay, I'm not only considering signal, I play with my s. So basically say, if my real part of my s is smaller than 0, my Laplace transform of this signal will exist. Question? So if sigma is larger or equal to 0, this limit will not exist. Okay. So you can't find the solution of this integral because this integral is an improper integral. Okay. So from this one, I can find the Laplace transform of constant 1 easily, and I know a normal transformation, Fourier transformation of constant 1 does not exist. Okay. And you have to know, to do this, I have two conditions. One is solution, one is this condition. This condition we call domain of convergence, which limited, okay, you have a region of my S, which is a complex number. In that region, my improper integral will be well defined. So it's very, very, because if you look at this one, by adding this sigma, which is my real part of complex number, I will have freedom. So this basically, if my sigma is positive, if my sigma is negative, I will have decaying function with me. So even this function itself, integral will not well behave, but multiply e power of is, I will have this part satisfied. Okay? So the key idea of Laplace transform is by playing with my real part of S, which is my domain of convergence, I can always find a well-defined improper integral of my Laplace transform. However, when you consider omega, because when you consider everything here, I'm writing down everything in this case. I'm just consider everything with positive signal. So this is, I'm dealing with a positive signal only has value when t larger or equal to 0. And this is my Fourier transform. So you can see this amplitude will not give me any extra information because for any omega, any of t, the amplitude of this one is always constant 1 because it will cosine plus g sine. However, if you have this term, so I can always write down xt e s plus g omega, no, sorry, sigma plus g omega t dt. So for any omega, any t, I can always write down in this form. So this part is original, my Fourier transform. Then by playing with sigma, I can add damping to my signal so that after damping, the integral or improper integral will have values or will be well defined. So that's the value of my Laplace transform because it adds extra freedom to let you have a damping of your signal so that your original signal does not satisfy. I can always write down as new signal yt, and it will be a new signal Fourier transform. And this new signal can be integrals. So from minus infinity to infinity, this new signal might be well defined, take absolute value because I have exponential decaying value. By choosing this sigma, I will have my freedom. So this is the difference. You can see. Okay, Laplace transform is simple to some extent. You didn't see j omega. It's very simple. It just has s. But you have to know I can't plot anything of my Laplace transform because my variable s is a complex number. I can plot a lot of things in frequency domain because my omega is real number. So that's why I can plot my spectrum, my omega amplitude, my omega, my phase. And if you have a complex number as your variable, you don't know how to get the spectrum of this one because this S is a complex number. Okay. Any question? So I can claim that any signal will have Laplace transform with appropriate region of convergence. So you can always find a region of my S, normally depends on my real part, so that in this region, this improper integral will be well defined for any signal. So there's no conditions for signal. Only condition, the condition convert to something related to S. And I can't claim any signal will have Fourier transform because I need to check conditions. Is that making sense? Okay. So that's a good thing because I know my step signal does not have Fourier transform. I know any periodic signal does not have my Fourier transform, then let me go back to Laplace transform. Okay. Questions? So, as I mentioned, the concept is very important. It's called region of convergence. And as also I highlight, because if you consider E power of minus st, and this one give you freedom to make system decaying or something, and if you consider E power of g omega, it will not give you any information because E power of g omega t take the absolute value of amplitude is always 1. And by playing with the real part of this complex number, you can make this improper integral reasonable or well-defined. Let's look at one example here. Okay. So I will have my xt is A minus beta ut. Okay. And now B belongs to R. Okay. First question is for this signal, whether my Fourier transform exists. So we know from chapter 3, okay, if my B is positive and my x omega, it will be B plus j omega. Okay. Okay. But if B is smaller or equal to 0, no, there's no Fourier transform, and generalized Fourier transform, I don't know, I have to check. Okay. And how about this system? Now, for any B belong to R, it can be positive, can be negative, can be 0. Okay. Let's look at this. So my xs will be from 0 to infinity and E minus beta, and I have E minus st and the dt. Okay. And you can see here, in this case, I will calculate this part is E minus B plus st dt. So this one, we do this many times, is B plus 1 minus 1 and E minus B plus S t, and my t from 0 to infinity. Okay. And I know I can always write down t equal to 0. It will be B plus S1 and minus B plus S B e power of minus B plus st, and my t should go to infinity. Okay, so again, this one is difficult. Let me try to do something simpler. I will take limit. So I will take limit capital T and B plus 1 E minus P plus S capital T, and I will write down my S which also my real part plus my j omega imaginary part. And in this case, I will write down is b plus s e minus b, capital T, and e minus sigma, capital T, and e minus j omega, capital T. And again, I will write down t goes to infinity, b plus s e minus b plus sigma, capital T, and e j omega, capital T. And if b plus sigma is positive, and my limit exists, and then limit t goes to infinity, everything here is always to be 0. Question, yeah?
So is the region of convergence for sigma for in the S domain, is it
Yeah.
sigma greater than b?
Minus b.
Minus
Yes,
b.
yes. So you can see here, and the domain of convergence is my sigma larger minus b. And you can see it's the same thing. So if I do the Fourier transform, I need b positive. And if I do in Laplace transform, I need my sigma, real part of my s, should be larger than minus b. So they are conditions, but the Fourier transform condition is explicit. You have to check this condition to find the Fourier transform. Laplace transform is implicit because it's hidden in the domain of convergence. So that's its key point. So you have to be careful, and everything, if you look at a lot of things in internet talking about Laplace transform tables, they always find a solution. So in this case, I can see if my sigma plus b is positive or sigma larger than minus b, this my xs will be b plus s over 1. So everything you see Laplace tables, they completely ignore the domain of convergence. But you have to remember this, they are domain of convergence because it's coming from the definition. And even right now, when sometimes I ask my PhD students about this, some of them, they don't know. Because this one is coming from, you need to understand why people introduce Laplace transform. They want to simplify the calculation. Get this one is not that difficult, but this one is very important in order to do the calculations. Okay. And we know that if b is positive, I will have my Fourier transform. And if b is positive, that means my sigma should be smaller. If my b is positive, my sigma should be larger than 0. So in that, we will have results saying, okay, the link between the Laplace transform and my Fourier transform. So basically, it says that, okay, if s equal to 0 is in its region of convergence, then if I let my sigma to be 0, I will have my Laplace transform will be same as my Fourier transform. So if in this case, if my sigma is 0, my s will be j omega, and they are equivalent. Basically, this condition is to guarantee that my Fourier transform exists, and if it exists, then I can always find, by substitute sigma equal to 0, these two equations are exactly the same. And you can see for this case, and so if b is positive, then 0 should be satisfy this condition. And this one, if b is positive, my Fourier transform exists. And in this case, my region of convergence, 0 is larger than anything. minus b, and my 0 is inside the domain of the region of the convergence, so that I can see my s equal to g omega. I can find the relationship between Fourier transform and Laplace transform. So it's very easy to say, because if you write my s by sigma plus g omega, you like sigma to be 0, it will be my Fourier transform under the condition that my Fourier transform exists. Is that making sense? Okay. Okay. So here, similarly, the are properties of Laplace transform. And it's very easy to write down, but anything missing here? Okay. Anything missing here? Okay. Every transformation for Fourier Laplace transform will have its region of convergence. So I have to make sure that, okay, I will have x1 region of convergence, x2 region of convergence. When I add them together, I will have overlap of my region of convergence, so that in this region, both this signal and this signal will have Laplace transform.
So only the overlaps.
Okay, so it's intersection, right? So what I'm saying is, so to be mathematically precise, all those properties are not well written. What I really need is, okay, I will have my x1t and my x1s and my region of convergence. What's my notation? Okay. And my x2t will have my x2s, and I have region of convergence x2. And I will have my a x1 plus b x2. I will have my region of convergence x1 intersect of region of convergence x2, so that I can have a x1s plus b x2s. Because in that region, both Laplace transform will be well defined. Is that correct? Okay. So I don't want to go through everything for the proofs if you pay enough attention to the region of convergence. So you can always try to reproduce everything, use the Fourier transform, assume those Fourier transform exist, and then trying to substitute my s by g omega. You basically can do everything here. It's straightforward. So the only thing I want to highlight, okay, is, okay, I'm not talking about this one first, is my derivative. Okay, the derivative is very, very funny, because you can see here, I will have my x dot sx, s, capital S, and I have something information of 0 minus. Okay, you might think, why? What happens? Because my Laplace transform takes integral from 0 to infinity. And why I should care about anything happens for something approaching 0 this way? Okay, that's mathematically it's long explanation, but let me simplify a reasonable explanation by showing something. you probably can see it. Okay, let's look at my xt, 1t equal to 1. Okay, my x2t equal to ut. Okay, so what's a step signal? 0, t larger, equal. So if I'm saying it's my u, 0, minus. So if you go this way, it will be this. So if I do Laplace transform, okay, we solve this one if my sigma am I correct? Sorry, it should be this. Yes. Right? So if I have region of convergence, I can find for signal this constant. And how about this signal? These two signals, if you look at them, they are different. Because one signal is from minus infinity to infinity, constant 1. And second signal from minus infinity to 0 minus, this part will be 0. And then at 0, it's a jump. And in this case, when I'm taking the derivative, I will have a jump at, so if I consider my u dot k, actually it will be my impulse response. Because I will have a big jump at t equal to 0. And in order to capture information, I really need the signal here to say, okay, what happens at here, because I need to take derivative, I need to know the information. So what I call the derivative, basically, so if I'm taking derivative at this part is 0, I should consider it's my u. So if I'm consider a derivative at u0, I have to think about what happens at t goes at 0 minus. That's one, when you take derivative and you take the Laplace transform, this information appears because you can see when I'm doing so if you look at this one and consider the definition of my Laplace transform, my definition of my Laplace transform will not consider the case anything before 0. However, when you take derivative, you need to consider the case of x0. So in this case, let me do things again. So okay, my x2t is my ut. Okay, I will use the definition of my x2 as will be minus 0 to infinity constant e minus st dt. Okay, so in this case, you will consider it's the same as my, if my real part of my s is positive, so that it will have decay. then my x2s will be 1 over s. So if you look at this signal, constant 1 and step signal, they do have same Laplace transform. And now, if I'm taking derivative, so let me use this one. Okay. For x1t is 1. What my x1 dot t? 0. Okay. Okay, so if I take Laplace transform of this x1 dot t, it will be 0, right? So I will use this notation for my x1 dot t. It will be 0. And then I will use derivative properties of my Laplace transform. Then I will consider, and this transformation is 1 over s. So I will consider this also equal to, I use derivative transformation, derivative property. I will have my s, 1 over s, and my x0 minus will be 1, minus 1. This one will be 1 minus 1, still be 0. Okay? So if you apply the derivative property, this is a correct one. Okay? Now, let's look at x2. So if I'm looking at my x2t is my ut, and my x2 dot t is my impulse response. Okay? And my impulse response, if I'm doing this one, and because this value will be not 0 for any t, only when my t equal to 0, so this one will be equal to this one. It will be constant 1. So for the impulse signal, Laplace transform is 1, and the region of convergence is everything. So for any s, this convergent, right? Yes?
In the definition of the Dirac function,
Yes.
it's from 0 minus to 0 plus.
Yes.
Here we're doing it from 0. It doesn't make a difference.
Sorry?
So if you go into, so by using the shifting property, right?
Yeah.
But the definition of Dirac is integral from 0 minus to 0 plus.
Yes.
But instead of 0 minus, we're doing it from 0 here.
Yeah, but the integral, the region is so small, you can always choose a point. The measure will be 0, so it doesn't affect my integral. Yeah. So in this case, I know my impulse response, and let me try to apply this one. So my Laplace transform of my x2t, which is my Laplace transform of my delta t, is my 1. Okay. Then I need to apply the derivative property, and this one I know is 1 over s again. So I have to consider is my 1 over s multiply s minus ut. This one is 0. So this one is equal to 0. So this also indicates it's correct. And if you don't have this part, then it's not correct. Because if you see that without considering this part, it might be not correct. So you have to consider, if you don't understand the derivative property, you will consider two signals. One is constant. One is, if you look, it's a step signal. So if you consider this one, very easy to consider. If you don't have this part, the result is not correct. You have to consider the value. And if at x equal to 0, t equal to 0 is not continuous, you have to consider all the signal beforehand. Because when you take derivative, it's current minus my beforehand information divided by small interval. So that's why This is very important. And any question? Okay. And from derivative, you can easily find the integral, because if I take the integral, this is my signal, and I call this signal is my x1t.